Type 2 hypersensitivities, we're talking about basically an antibody in the serum essentially binding to host cells, and they're binding to the host cells through this antigen that's going to be on our host cell. So just walking through this mechanism, let's just say in this situation, our host cell is going to be our red blood cells, right? And we'll say that, there's some antigen on the red blood cell. Now, this could be because we have a certain pathology like autoimmune hemolytic anemia, for example, right? This AIHA, or this could be secondary to, a drug that we took. Maybe we took a drug that bound to the surface of our red blood cells and now is causing us to target our red blood cells. Okay, so let's just say for simplicity's sake that we took some drug, right? We took some drug, let's just call it penicillin, for example. So let's just say that we took some penicillin, and that penicillin had an antigen. Okay, that's kind of what you see here. So that's this antigen, and it bound to the surface of our red blood cells. Now, this antigen from the drug is going to be foreign to our body, and so we can generate antibodies against that antigen. And you might be saying, well, which antibodies are we talking about? Classically, when we're talking about type 2 hypersensitivities, we're usually talking about IgG or IgM. And again, you want to juxtapose that to what we talked about with type 1 hypersensitivities, where that was primarily IgE. Okay, so usually this antibody that's doing the work here, it's usually going to be IgG, but in some cases, it can also be IgM, although that would be a little bit less common. And so again, it's also important to know what's binding to what, right? So when I have an antigen, my epitope is usually going to get bound to the Fab portion of my antibody, right? My Fab portion, and then here you can see this is going to be your Fc portion. Okay, so again, I'm going to bind to this antigen on a surface of one of my cells. In this case, it's the red blood cell. And you can see, here's the antibody, right? There's the Fab portion. There's the Fc portion bound to this red blood cell, bound to the antigens. Now, what happens is when I start binding antibodies to host tissue, the body can think potentially that this structure is foreign. Similar to what happens if you have a bacteria, right? If you just think about, okay, if you had some bacteria here, right? You had some bacteria here and you wanted to target this bacteria. Well, on this bacteria, there would be antigens, right? We would target these antigens, and then we would have antibodies that would come in, similar to what you see here. And these antibodies would come in and attach to these antigens and essentially stimulate complement, neutrophil chemotaxis, etc. So all the things that we talked about in the last videos, the only difference is instead of targeting this bacteria, we're targeting our own cells, because our own cells have some antigen on them, either from a drug we took, from some genetic pathology potentially, right? Or some other things that we'll talk about. But that's the point. So the point is now we have this antibody bound to this antigen, bound to this host cell. And the questions come in where you have to know, well, what are the things that can potentially happen to this host cell? Okay, so there's really 4 major things. So let's go through those really quickly. So the first thing is we can go straight down that complement pathway. You can go back to the complement video, check that out. But essentially what we have here is we have complement binding. Remember, it's going to bind to the Fc portion of the IgG antibody here, and that can essentially lead to cell lysis, right? Eventually, if we get to the MAC complex, which is the terminal complement cascade, we can essentially use this MAC complex to essentially punch holes into this red blood cell and destroy it. Okay, so that's one option. So by having these antibodies attached, we can have complement cascade stimulated, and the terminal endpoint of that would be the membrane attack complex, C5b to C9. Now, the other option here is, remember, as I'm stimulating complement, I can also end up with opsonization, right? So instead of going to the terminal component of this membrane attack complex, I can stimulate C3b specifically. And C3b can then kind of drag in some of these phagocytic cells to essentially opsonize this red blood cell. And the end result is pretty much the same thing, right? We're going to destroy our own host cell that has this antigen bound, only it's a little bit different pathway. It's through C3b. Remember, that's particularly high yield. Remember, C3b associated with opsonization. And you can also remember that we talked about IgG is also associated with this pathway. And guess what's bound to the surface of these cells? IgG in most cases, right? IgG. And so IgG, like we said, is also very much associated with opsonization, and that's where this all comes together. C3b, opsonization, IgG, opsonization. Third thing on here is chemotaxis. Okay, so remember, again, going back to your complement cascade, C5a is going to be a very important chemotactic factor in conjunction with LTB4, interleukin 8, right? Those are really important neutrophil chemotactics, and those cytokines can essentially stimulate neutrophils to come to the site of wherever this antibody might be, right, with this complement, right? You might have chemokines getting released to these red blood cells. And these neutrophils, when they get to these red blood cells, they're just going to dump peroxidase and a lot of these really toxic chemicals on the red blood cells to destroy them. Now remember, we're targeting, in this situation, one red blood cell. When we talk about type 3 hypersensitivities, we're talking about like an entire region of the body or entire organ potentially that's going to get targeted. And so you can imagine that chemotaxis and complement-mediated C5a release is going to generally be much higher when you're targeting a whole organ, for example, like the kidney. In this situation, if we're just targeting red blood cells, you're not going to get as many neutrophils to the scene because these red blood cells are always moving around. So these neutrophils will play a little bit bigger role when we talk about type 3 hypersensitivities in terms of the damage that they can cause. And the last one on here is the natural killer cell. Now this ADCC, antibody-dependent cell-mediated cytotoxicity. And this is largely driven by natural killer cells. And what this essentially means is, the name kind of gives it away in a sense, antibody-dependent, right? We need this antibody here. This antibody will essentially bind to this receptor on the natural killer cell. So it's dependent on an antibody and it's cell-mediated cytotoxicity, meaning the natural killer cells are going to mediate the destruction of this cell. Kind of similar to what happens with the neutrophil, but not exactly the same because there's not chemokines necessarily that are stimulating this natural killer cell to come over here. This natural killer cell is binding to the IgG receptor here and then releasing perforins and granzymes to essentially destroy the red blood cell. Okay, so just remember, these are your four kind of major pathways, and a lot of this is really complement mediated. I mean, if you're just looking, just trying to remember this, you can really remember that this is a large portion of the cell destruction that's happening because we're binding to our own cells is mediated by complement. You just have to be familiar with your complement cascade. This all goes back to the complement video. We're just kind of adding a layer to that, and then also be familiar with antibody-dependent cell cytotoxicity that's largely driven by antibodies that are bound to cells, and then remember that it's the natural killer cells that are going to come and bind to those cells and then destroy them. The other thing that natural killer cells are very notorious for is binding to cells that don't have MHC1. Remember, all of our nucleated cells should have MHC1. So when cells are downregulating MHC1, that could indicate potentially that there's a cancerous process or something wrong with that cell, and natural killer cells step in and then destroy host tissue in situations where those MHC1 complexes are downregulated. So the two big things to remember, again, for natural killer cells, two big things to remember is that they're going to target cells through antibody-dependent cell cytotoxicity, and then also they're out there searching for MHC1. And if they find a cell that doesn't have it, then they're going to destroy it. Okay, so those are the big things. Let me clear this up here. Those are the big things for natural killer cells to remember, if you had to remember anything. Okay, so let's run through this really quickly. So again, this is sometimes referred to as a cytotoxic process, right? A cytotoxic hypersensitivity. Why is it cytotoxic? Because we're destroying cells, right? Cytotoxic, cell toxic, we're destroying cells. And the way this happens, like we said, we're going to have an antibody. That antibody is going to bind to our own host cell surface through an antigen, okay? Or there'll be graft tissue, which we'll talk a lot more about in the transplant rejection video. Again, 4 processes. A lot of this, like we said, really just mediated by complement. So if you're familiar with your complement cascade, I think this will make a lot of sense. So C3b, C5a, ADCC, we all kind of talked about that. Now, you should also know kind of what pathology falls into, each category of hypersensitivity. So autoimmune hemolytic anemia, very classic for this type 2 hypersensitivity, where you have antibodies that are binding to your red blood cells and eventually causing complement-mediated lysis and ADCC of those cells. The same thing is true with your platelets. You can have immune thrombocytopenic purpura, right, ITP, acute hemolytic transfusion reactions. So this is very classic if you have a patient that receives blood from somebody else and they're not matched, right? If you have mismatched blood being donated, right, and then given to a patient, right? So this is going to be mismatched blood. Is very classic for this. Obviously, we do a type and screen whenever we donate blood. I mean, emergent situations, they'll sometimes use O negative, but in general, we're trying to match the blood so we don't run into the situation. Like I said, I'll talk about this one in more detail when we come to it. But remember, the concept is the host has antibodies to certain markers on red blood cells. Depending on what the person's blood group is, they could have antibodies to other types of red blood cells, right? And so when you give those red blood cells, those antibodies then, what do? They can bind to this donated red blood cell, right, that has these different markers on it and then can target it for destruction, and you can end up with a transfusion reaction. The other thing on here is erythroblastosis fetalis, and this is sometimes referred to as the hemolytic disease of the newborn. Okay, so we'll talk about this probably in its own video, but just to give you a high-level overview, essentially what we're talking about here is, and let's clean this up a little bit. So essentially what we're talking about here is certain red blood cells in mom. So I'm just going to put mom here. Okay, so certain red blood cells in mom can have markers on it. Okay, so we'll call this an RH marker. Okay, so we'll say Rh positive, and then we have fetus over here. So we have mom and then we have fetus. Now, if mom's Rh positive, generally she won't have antibodies against this factor, because if she did, she would then be destroying her own cells. Okay, so usually if mom's Rh positive and baby's Rh positive, everything's okay. But let's imagine that instead of mom being Rh positive, if mom's Rh negative on the other hand, what that means is mom doesn't have this antigen on her red blood cells, but baby has it, right? And so what mom might do is mom might say, hey, mom's body might recognize this antigen as foreign, okay? Because mom doesn't have that on her cells, but baby does. And so what mom would do in this type of situation potentially is mom might start to generate antibodies against this Rh factor. Now remember, in the placenta, we talked about this, there's only really one major antibody you need to remember that crosses the placenta, and that antibody is going to be IgG. And what are we talking about right now? What's the major antibody here? We already said IgG, right? If this is the first baby, right, this is fetus number 1 that's Rh negative, it's going to take mom a little bit of time to go through class switching to generate IgG antibodies. Remember, her IgM antibodies aren't going to do a really good job of trying to get through the placenta because they're so big, right? They're pentameric, at least a lot of them are. Okay, so this first baby is not really going to get affected. But what's going to happen is mom's going to start to generate antibodies. There's going to start to be class switching against these antigens. They're going to get presented essentially to mom. Okay, and you're going to start to get T cell activation, memory response, all those things we talked about in the previous videos. And so mom, from this first fetus, will start to make antibodies. For baby number 2 though, okay, so baby number 2, let's say mom has a second baby. Okay, let's say this baby is Rh negative. So if this baby is Rh negative, it's unlikely that mom would target this baby with antibodies, right? Because there's nothing to target. This antigen isn't there. There's nothing for the antibody to bind to. Mom's Rh negative, baby's Rh negative. So if fetus number 2 is Rh negative, we wouldn't have anything to worry about. However, if fetus number 2 is Rh positive, right, just like baby number 1, now we have that antigen on here again. And now mom's antibodies are ready to go. Mom already class switched. She already has a memory response. These IgG antibodies are going to go right through the placenta and right to fetus number 2 and start to bind to this antigen. And it's going to look just like what we saw here. This would be your Rh positive antigen, right? That's what's in yellow here. And then here's your IgG antibody. And we would go through all of the same process that we talked about right here. We'd have baby cells getting targeted and getting destroyed. And this is obviously a very serious situation. Okay, and we won't go into any more detail than that for this video, but that's really the mechanism, the idea of what you want to have when you think about erythroblastosis fetalis. Now, there's other examples here that are more inflammatory in nature. When I say more inflammatory in nature, I'm talking about more involvement of kind of a general tissue, but we don't have complex formation. The thing that defines type 3 hypersensitivity is that we start to make these complexes with the antigen and antibody. In type 2 hypersensitivity, most of the stuff we're just targeting single cells. But here, if we're targeting kind of an overall structure, for example, in Goodpasture syndrome, we're going to target type 4 collagen in the lungs and the kidneys. Okay, and so because there's not complexes, though, it actually goes into this type 2 hypersensitivity category. Okay, so again, you want to categorize these diseases into these different hypersensitivities. The same thing is true with rheumatic fever. Hyperacute transplant rejection is actually quite similar to the hemolytic reaction. Remember, when you start to transplant tissue, everybody has different HLA markers. You have to match up your HLA phenotypes. If you have a different HLA phenotype, when I put a graft in another patient, right? So here's my host or my recipient, right? You can call it either one, my host or my recipient. And then you have your donor, right? You have your host and your donor, okay? And the donor is going to give the host something, right? They're going to give them some kind of transplant. Let's just say, the donor, we're doing a renal transplant, right? So the donor is going to give their kidney to the host, okay? So now the host is going to have the donor kidney, okay? But remember, the host is going to have different HLA markers, right? So the host might have one HLA marker. Let's just call this person HLA-A just for simplicity's sake, and let's just say that this person is HLA-B, okay? So if they have different HLA markers, those markers on the cells, right, this HLA-B marker on this kidney tissue might be foreign to this host who only has HLA-A. And so for that reason, this host might already have some antibodies against HLA-B, right? They don't have any HLA-B in their tissue. This is foreign to them. And so they already have these antibodies. They can bind to this tissue and essentially mark it for destruction. And again, this can lead to complement activation. We can have thrombosis of these vessels because of the infiltration from all this tissue and the inflammatory response. And that can also be problematic. And we'll talk about that more, like I said, when we go through the transplant rejection.